Good morning or good afternoon. My name is Professor Duke Orata. We are continuing with our thermodynamics lectures. Today I want to look at this exchange between two black bodies. The exchange between black bodies. By now you know what a black body is. We have discussed this in a series of lectures, and I continue urging you, humbly requesting you to go through those lectures so that we are all moving together in a synchronized way. Now, suppose we have two black bodies and they can see each other. In other words, there is connection between them. Forget about the fact that there is gas between them. We are assuming that those gases don't absorb any of those radiations, and so even if they did, it doesn't interfere with us. So let's say there were two black bodies. Let us say we have two black bodies, and the elemental areas are dA1, dA2. So this is A1, and A2 at temperature T2, and this A1 at temperature T1. And let us say that the difference, the distance between those two black bodies or the elemental areas is x. Let's call that x. Let's call that distance x. Between those two black surfaces. Now, we are assuming that the normal of this elemental area, dA1, that normal there is inclined at some angle, let's call it phi 1, to the line joining the two bodies, that is x. And the normal of the second elemental area is inclined at some angle phi 2 to the line x joining the two. So let's just say down something. So we have two black bodies seeing each other. Assuming we have two elemental areas, dA1 and dA2, separated by a distance x. And secondly, the most important assumption, we have said that the normal to those elemental areas are inclined at certain angles. For one, it's inclined at angle phi 1, for two, at angle phi 2 from the line x joining them. The normals to the two elemental areas dA1 and dA2 are inclined at angles phi 1 and phi 2 with respect to line x. Very important that the normal is inclined through an angle phi 1, that's for elemental area 1, that for elemental area 2, phi 2. Now, the elemental area dA2 subtends a solid angle d omega 2 at dA1. Let's just take note of that. And you already know when we are talking about angle subtended, you already have worked with that in the other lectures, and so you know what it is. So if the elemental area dA2 subtends solid angle d omega 1 at dA1. Then you know that d omega 1, you already know that from our earlier lectures, will therefore be the elemental area 2 over x squared, that distance between them, cosine of phi 2. Similarly, the intensity of radiation from dA2, the intensity of radiation from dA1 to dA2 can be gotten just the same way we did in the others. The intensity of radiation from dA1 to dA2 is given by radiation from dA1 will be I cosine phi 1. You already know that, as we talked about in Lambert's cosine law. So please, once again, I encourage you to go through those lectures. And number 2, the radiation from dA1 incident on dA2. The radiation from dA1 incident on dA2. That radiation will be given by dQ1 will be IN1 I1, and you know what I1 is. Then we'll have dA2 over x squared cosine phi 2 dA1. So we can put in the value for that intensity so that the radiation incident on dA2 from dA1 will be equals to I. We have I1, that's intensity 1, we have it there. Will be IN1 cosine phi 1, and we have cosine phi 2 over x squared. We have dA1 dA2. That's the radiation incident on dA2 from dA1. Now, in the same way, the element dA1 subtends a solid angle also at dA2. The elemental area dA1 subtends a solid angle d omega 2 at dA2. So that d omega 2 will of course just the same way dA1 over x squared cosine phi 1. And once again also the intensity of radiation from dA2 to dA1 will again be given in the same way. That's the intensity of radiation from dA2 to dA1 is again given by I2 will be IN2 cosine phi 2. And of course the radiation from dA2 incident on dA1 will again be given the same way. The radiation from dA2 incident dA1 will be given by dQ2, and of course the black bodies, so let's have that B there to indicate the black body, will be given by I2. So we now just substitute directly because we're just repeating the same process there. For I2 is I N2 cos phi 2. We have IN2 cos phi 2. Then we have dA1 or x squared cos phi 1 dA2. So we will need this last quantity, so I want to erase it so that you don't have to go again to the derivation. So dQ2b is IN2 cos phi 2 cos phi 1 dA1 dA2 over x squared. Now, remember when we talked about intensity, we combined both Boltzmann law, and we also had the Lambert cosine law. And so we said that from Stefan Boltzmann law, and Lambert cosine law, In, intensity of is basically sigma per 4 pi. Just go through our earlier lectures, then you're going to see that you have this. Of course, that is Stefan Boltzmann constant, that's absolute temperature. Absolute temperature. So, the intensity, so if you have dQb to be minus dQ1b, then we are going to have In2 minus In1 into cosine of phi 1 cosine of phi 2 dA1 dA2 over x squared. So we've just subtracted the intensities of radiation on both elemental areas. And this is intensity, so we can plug in that quantity which we got from Stefan Boltzmann law and Lambert cosine law, so that we have, we put that place of intensity, then we have dQ2b minus dQ1b will be equal to sigma over pi into cosine phi 1 cosine phi 2 A1 A2 over x squared into t to the power 4 to 1. Let's write it out properly. The space is not sufficient, so let's write it properly. So we are saying therefore dQ2b minus dQ1b will be sigma over pi into cos phi 1 cos phi 2 dA1 dA2 over x squared into t 2 to the power 4 minus t1 to the power 4. Now, you have to do double integration for this quantity to solve some of these values here. But you can choose the simple way. If we assume that the elemental areas are very small, they are flat, the distance between them is big, the distance between them, that is x, is is reasonably big, then we can do some approximations. If we assume the elemental areas dA1 and dA2 are flat and separated by a large distance, and the temperature relatively uniform. So if you make that assumption, then we can assume values for A. We can use the areas A1 and A2, and also, in addition to that, we can estimate phi 1 and phi 2, and we'll be home and dry. We'll be able to calculate the values involved here. So in that case, therefore, we can use values for A1 and A2 and assume values for phi 1 and phi 2. Then you can calculate the quantities. We can calculate that particular quantity. You can calculate the energy exchange between those surfaces. But you have to assume that the elemental areas are very small, the distance is large, the temperature is relatively uniform. Then you can assume. Otherwise, you have to do double integration. So let's stop at that particular point.